Last episode, we turned a flat pile of chunks into a graph, entities as nodes, relationships as edges. Now, the payoff. That structure lets us answer questions a vector index can't. Because here's the thing nobody tells you. Your users ask two completely different kinds of questions, and a single retrieval strategy quietly fails one of them. The first kind is local. Tell me about the transformer. That's a question about one entity and the things sitting right next to it. You don't want the whole graph, you want the neighborhood, a couple of hops out, and nothing more. This is the part plain vector search struggles with. Take a question like, how does the transformer connect to retrieval? That needs more than one hop, what people call multi-hop. You go transformer to GPT, then GPT to RAG. That's two edges across the graph. A plain similarity score over flat chunks can't follow that chain. The graph can because the chain is literally a path. The second kind of question is global. What topics does this whole corpus even cover? No single neighborhood answers that. You need to step back and find the clusters, the tight knots of entities that talk mostly to each other. That clustering has a name, community detection. Once you have the communities, the global answer writes itself. Summarize each one. This community is about model architecture, this one about serving, this one about retrieval. That's the shape of graph RAG. Local questions walk a neighborhood, global questions summarize communities, and you route based on which you're asked. Let's build a tiny knowledge graph by hand, so the structure is honest and visible. 12 entities, 3 topics, plus a couple of bridge edges so the clusters aren't islands. The retrieval here is all real networks. Only the final one-line community summary is a fixed stand-in for an LLM. Same words every time, and I'll mark that line when we reach it. For the local question, ONNX ready go graph, G, transformer, radius of 2 returns the 2-hop neighborhood as its own subgraph. Radius 2 means include everything within 2 edges, the entity, its neighbors, and its neighbors' neighbors. For the multi-hop test, nx.shortest finds the chain from transformer to RAG. It comes back as transformer to GPT to RAG, 2 hops, and we assert the target is actually reachable because a retriever that silently returns nothing on a valid path is worse than one that throws. For the global question, greedy modularity communities, G, clusters the graph. It groups nodes so that edges stay mostly inside groups, not across them. We sort the clusters and for each call our summarize helper. That helper is the one mocked line. In production, it's an LLM prompt. Here, it's deterministic, so the output reproduces. Run it. The graph reports 12 nodes and 17 edges. The 2-hop neighborhood of transformer holds 6 nodes. The multi-hop path lands at 2 hops through GPT, and community detection finds 3 communities of 4 entities each: model architecture, serving and infra, retrieval. And the figure says exactly that. 3 colored blobs, 4 nodes apiece, matching the 3 communities in the log. A highlighted 2-edge path from transformer through GPT to RAG, matching the printed hops too. Figure equals terminal. The structure on screen is the answer. 2 questions, 2 walks, 1 graph that serves both. Next episode we put every stage together, package, serve, optimize, retrieve, graph, and ship the whole thing end to end in the capstone.